Okay, this is the last section in Chapter 3, and it's starting to transition us more to the material we'll be doing in Chapter 4. So up till this point, we've always started with a function and taken derivatives. So given a function, we have a lot of rules, and we can produce its derivative. Given f, we get f prime. So those rules are like the power rule, the quotient rule, the product rule, the chain rule, derivatives of trig functions, etc. So we know how to do that. That means if you give me a function that is describing something, I can take its derivative and tell you the rate of change of that function with respect to the variable. That's what the derivative is. So you describe to me the y values on a graph. I can take the derivative and tell you the slopes of the tangent lines on the graph. If your function tells me position, I can take the derivative and tell you velocity. If your function tells me the population of some population, I can tell you the growth rate of that population by taking the derivative, and so on. But now what we want to do is go the other way. That is, if you describe for me the slopes of some graph, I would like to be able to tell you the function, the y values. If you describe for me the velocity of an object, I would like to be able to give you the position. Or in other words, if you give me f prime, I would like to be able to figure out what f of x was. So not taking a derivative, but sort of untaking a derivative, going backwards. The question is, how do we do that? Before we talk about how, we need a little bit more language. So this process of going backwards, given f prime, we want to find f, that's equivalent to, given a function, f, we want to go back and find a function, capital F, whose derivative would be the original one we got. So you give me a function, little f. I want to find another function, big F, whose derivative is the function you provided. Okay, that capital F function is called the antiderivative of the little f function, because it is not the derivative of it, it's sort of the other direction. It's going backwards, untaking a derivative. It's the antiderivative. And this equation here, big F prime equals little f, says that the derivative of the antiderivative is the original function. Okay, so here's an example. I have a function f of x equals x squared. Let's find an antiderivative of that function. That is, I want a capital F function whose derivative is x squared. I can do this by trial and error. I know that when I take derivatives, the powers go down, so when I take antiderivatives, the powers ought to go up. That means my first guess might be something like x cubed, right, if I want its derivative to be x squared. Does that work? Well, no. If we try taking the derivative of that, we don't get x squared, we get 3x squared. So that's wrong. X cubed is not the antiderivative of x squared. But it's almost right. I want x squared, I got 3x squared, so maybe I just need something a third as big. So what about capital F of x equals 1/3 x cubed? Does that work? Yes, it does, and here's why. When you take the derivative of that function, the 1/3 times 3x squared gives you just x squared, which is what we wanted. Remember, we wanted capital F prime to equal our original little f. We want the derivative of the antiderivative to equal the original function. So capital F of x equals 1/3 x cubed is an antiderivative of the function f of x equals x squared. Okay, but notice that in the question and in the answer I said an antiderivative. I didn't say the antiderivative. When we take derivatives, we say what is the derivative of this function. But here I'm not saying what is the antiderivative, I'm saying what is an antiderivative. And the reason is because there are more than one possibilities. There's lots of possibilities for antiderivatives. In our example, with little f equals x squared, one antiderivative was 1/3 x cubed. But a different function, 1/3 x cubed plus 154, would also have worked. Right? All I need is for its derivative to equal x squared, and when I take the derivative of this, 1/3 x cubed plus 154, I get 1/3 times 3x squared, and then the derivative of 154 is 0. So I do in fact get x squared. That means that I have two different functions that are both antiderivatives of x squared. In fact, there's nothing special about 154. 1/3 x cubed plus any constant, any number, will work as an antiderivative. So there's infinitely many possibilities for an antiderivative of f of x equals x squared, right? 1/3 x cubed plus any constant number. So a natural question is, maybe there are even more. Maybe there are other antiderivatives that aren't 1/3 x cubed plus a constant. But in fact there aren't. And here's why. It comes in the form of a theorem. This theorem says, if I have any antiderivative of f of x on an interval, then all the other antiderivatives have to be just like mine, but plus a constant. How do we prove that? Okay, well, we start with the assumption that we have an antiderivative. We know capital F is an antiderivative of little f, so capital F prime equals little f. The theorem says something about all other antiderivatives, so let's say we've got another antiderivative, and we'll call it capital G. It's another capital letter, so it'll be another antiderivative, and it's an antiderivative, so that means it prime equals our original little f. So G prime equals little f as well. Now let's look at what the difference is between our other antiderivative g of x and the one we started with, capital F of x. So we'll take that difference, g of x minus f of x, and we'll take its derivative. Okay, g of x minus f of x prime, well, I just take the derivative of g minus the derivative of f. That's how derivatives work with addition and subtraction. And both of those derivatives were little f of x, because they're both antiderivatives of little f. And so what I get is 0. But hang on, we had a function about if you have we had a theorem about if you have a function whose derivative is 0, then something. Okay? There was a theorem at the end of section 3.2. That was the section on the mean value theorem and Rolle's theorem. So the theorem at the end of it said, the only functions whose derivatives are 0 are constant functions on an interval. So I have a thing here, g of x minus f of x. Its derivative is 0. That means it, g of x minus f of x, has to equal a constant. And that means g of x equals capital F of x plus c. And that's what I wanted to prove, right? I wanted to prove that if I start with an antiderivative capital F, any other antiderivative has to look like capital F plus a constant. So I started with an antiderivative capital F. I said g is any other antiderivative, and look, it's capital F plus a constant. So any other antiderivative of little f has to be the one I started with, capital F, plus some constant. That means if you start with a little function and you want to find all antiderivatives of it, all you need to do is find one antiderivative, any one, and then add a plus c, right? Because any antiderivative will be your antiderivative plus some constant. That's called the general antiderivative of f of x, right? The general antiderivative is something that looks like some function plus c. There's nothing special about c. You could do plus d or plus k or plus any letter you want to use. The point is plus a constant. So the general antiderivative is an antiderivative plus a constant. For example, in our earlier example, little f of x equals x squared. The general antiderivative is 1/3 x cubed plus a constant, because we know that one of the antiderivatives was 1/3 x cubed, and so then I just add plus c. We'll do many more in class, and we'll start figuring out some antiderivative rules. So we know derivative rules, we'll start figuring out rules to go the other direction. In general, these are harder, but there are some simple ones that we'll start with. Here's the video question. Find the general antiderivative of f of x equals x. Remember, that means you need to find a function whose derivative is x, and then add a plus c. All right, I'll see you in class.